Hi, Calc AB students, getting ready for your Chapter 4, Part 1 exam with this practice exam. So let's take a look at problem number 1. So problem number 1, you're working backwards here. You're saying that I have this derivative and I want to see if I can figure out what the function is. So what I would do is this. You see we have the f prime terms on the bottom here. So this requires that we think backwards. So I know that if I have a term of 3x squared for the f prime terms, that means that the power on f has to be x cubed. Going straight across the top row that you see here, if I have negative 8x for the middle term, then the power has to be 2, or the x squared power. And if I have a negative 6 constant in the derivative, then the power has to just be x to the first power. Now, if we have a constant and we don't know what we have here, we have a constant, we take the derivative, we're going to get 0. So that would be blown out of the f prime expression anyhow. So we could use any constant in for f. So what our job is, we have to figure out, we're going to take the derivative of our power and see what missing factor we need. So you see in green, in the next row, the middle row, I'm going to take the derivative and include the derivative of the power, and I'm going to include the missing factor there. So if you look, we have 3x squared for the first one. That is our f prime first term, so I just need a 1 there for 1x cubed. That'll be the first term of f. And then to take the derivative of x squared, I get 2x. I'm missing a factor of negative 4, so I need a negative 4 in the power. If I take x and take the derivative, I just get 1, so I actually need a factor of negative 6 as the coefficient of x. And then I have a plus c that's going to end up as our constant in our function for f, because the derivative of the constant is just going to be 0. So it says find all possible functions. This is what we refer to as a family of functions in the answer for number 1. Okay, so they're a family because the constant c is just going to cause that vertical shifting of x cubed minus 4x squared minus 6x. Okay, all right, that's number 1. Okay, number 2, find the extreme values of the function. In this case, we're actually going to use the first derivative test for this, but it doesn't say the first derivative test. But we're finding the extreme values, and it's not on a closed interval. So you guys should know this because it is a quadratic, but I'm asking that you do the calculus work to show this. If you can work with these functions, you can work with any functions. Okay, so you've got a quadratic, so you know the first derivative is given, and set it to 0, get your critical numbers, put them on the number line. So on the top above the number line, I put the sign of the derivatives using the test points on either side of the critical number x is equal to 2. I find out that the function is decreasing, then it's increasing at about x equal to 2. So then to answer the first question, I'm going to find the extreme value, select the correct choice. There is no absolute or local maximum on this graph. It's just going to go to infinity as x goes to positive or negative infinity. So then the second part of this, we have an absolute minimum, and that's at the vertex of the parabola, is 2. Now keep in mind, this is a y value here, a y value at x is equal to 2. So when we talk about the minimum value of a function, it is a y value. But very often we're asked to state it as an ordered pair, if you will. Okay, so that's all the work that we need here. Notice that you want to show me what the value of y of 2 is in that case, okay? Prove where your critical number is coming from and so forth. Put it on a number line, test the derivative and so forth. Okay, got to stop saying so forth. Number 3, use the concavity test. So it's pretty much what you do with the first derivative test. And you're testing for the sign of the derivative. Now, if you notice, I take the first and then take the second derivative and then set it equal to 0 because the second derivative is never undefined, and I get the possible POIs. That doesn't mean there's a POI here, but I'm looking in this case, determine the intervals on which the function is concave up or concave down. I'm not being asked for a point of inflection, but it helps me to see where I'm going to have a change in the concavity. So you can see that I put it on a number line. F double prime goes from negative to positive. Where F double prime is less than 0, our graph is concave down. Where F double prime is greater than 0, it's concave up. So that's how you would handle that, answer the question. So this differs from increasing, decreasing intervals that we don't include the endpoint because at the endpoint is where the concavity the second derivative is 0. It's not greater or less than 0. Okay, so number 4, the first derivative test use the first derivative test to determine the local extreme values of the function. So even though you know it's going to occur at the vertex, and it's pretty easy to find the vertex without using calculus, we're going to take the first derivative, set it equal to 0, get the critical number, put the critical number on a number line, get test points to the left and right. Our critical number is 1/8, so we're using 0 and 1, plugging in. We get that the derivative here, I'll put this up here, y prime is negative. So y prime is then good. What are we doing here? The first derivative test, right? So you got to think, okay, I need to know that it's y prime is less than 0. Let me hit that. So I have a y prime there, and y is then decreasing, and y prime is greater than 0, so y is increasing. Okay. So we need to find then, we find what y of 1/8 is. It turns out to be negative 81/16. So we know that there's a local minimum that occurs at that point. Okay, there's the arithmetic that goes along with that. Kind of good to practice a little bit of that if you're out of the habit of doing that. Where's the local maxima? There are no local maxima. Okay, and you can see that on the number line that you can see the slope is negative and then goes to positive. So the only way this is going to behave is like that. All right, so then it says the function has an absolute, identify any absolute extrema. So the local is the absolute here, and that's has an absolute minimum of negative 81/16 and has no absolute maximum. Okay, so there's that, number 4. Number 5. Number 5 is interesting because we have that derivative, k. We have the function k of x, and then the derivative involves negative 6x to the 5th power times the exponential function e to the negative x to the 6th. So using the principle of zero products, we would find the critical numbers then, and we only have one. It's just x is equal to 0 because negative 6x to the 5th is equal to 0, or e to the negative x to the 6th. It's never going to be 0, so we don't have to worry about that. So it's only x equal to 0 for our critical number. Now, when we're looking at this, we are not doing the first derivative test. We're doing the candidates test here. So we need to compare the k of the endpoints with the k of the critical numbers. When we do that, we're finding k of negative 3, k of 2, and k of 0. Can we do that? The biggest, this is the largest value that your function is going to have on that interval, 1. And these two, you can see 1 over e to the 3 to the 6, that's going to be e to the 729th power. And that's certainly going to be smaller than 1 over e to the 2 to the 6th power. So 2 to the 6 is 64. It'll be 1 over e to the 64th power. That's not going to be as small as e to the negative 729th power. So there you go. There you have it. The absolute min. Here's the absolute maximum value on. So you just compare them. In that case, find your critical number. Compare it with compare k of the critical numbers with k of the endpoints. Okay, and the last point, identify any critical points that are not stationary points. There are no critical points that are not stationary points because k prime of 0 is going to be equal to 0, and that means the stationary point is at 0, 1. Okay. All right. Next question. For the given function, state whether or not the function satisfies the hypothesis of the mean value theorem. So in this problem, as I read it, and if it does, find each value of c on the interval a, b that satisfies the equation. So first part of that we have to look at, we have two conditions for the mean value theorem, that f is continuous on the closed interval a, b, and it's differentiable on the open interval a, b. In this case, the interval is negative 3 to 1. So it's a polynomial, so it definitely is. Okay, we don't have to worry about anything else other than, hey, go forth and let's get the mean value theorem. So we've got f prime, and then notice we're using f prime of c here. All you have to do if you're looking at this, it doesn't really matter what variable you have, except they're saying f prime of c, so I'm going along with the theorem, the mean value theorem. So I have 8x minus 4 is the derivative, so 8c minus 4 is equal to f of 1. And remember, the mean value theorem guarantees that the instantaneous rate of change is equal to the average value, the average rate of change on the interval, as long as it's continuous and differentiable on that interval. So simplifying that, I get f of 1 is negative 3, f of negative 3 is negative 45 over 1 plus 3, 4, and solve for c. Okay, so the value of c that satisfies that is negative 1. Okay, so you're good to go there. Next problem, particle moving along the x-axis. find the velocity and the acceleration, and then describe the motion of the particle. The first two are kind of the least involved there. You have the using the power rule with that. So you have v of t and a of t given. Then we want to describe the motion of the particles. So we have to use some information about both the position function and the velocity function. So in this, describing the motion, the particle begins t equals 0 is that time at position -9. And you can see above I have x of 0 is equal to -9. Okay, and then it's moving in the positive direction, and that's because v of 0 is equal to a positive 12. The sign of the velocity is positive, therefore you're moving in the positive direction. It moves to position 7 at t is equal to 2. So t equal 2 is a critical number for the velocity. Velocity, remember, is the first derivative x prime of t. So I want to check out where I'm at because it's saying it moves to position. So I need the position at 2. And if you notice here, I crossed out -2 because it specifies in the problem that t is greater than or equal to 0. So I only have to count the 2. Finding the position at 2, then I get 7. So that's what the problem is asking. So it moves to position 7 at t is equal to 2 and then changes direction, moving in the negative direction. I put a number line down here so we can test the velocity if I use a test point of 0 to the left. And you already know this. It's negative. Oh, wait a minute. Hold it. So v is positive, right? V is positive. Looking at the wrong thing for a second. And that can kind of happen. I'm like making sure that I'm trying to look at the right function here. So I wanted to make sure x prime is equal to v. So you start off, remember the velocity at 0 was 12, so that's positive. And then after 2, let me draw this line here. After 2, I'm using 3, and I end up getting a negative velocity, which means there's a change of direction at that point. All right, so then with that would mean I'd plug it. I'd find what v of 3 is here just very quickly. But just by observation, it's not too hard to understand that that's going to be -3 times 9, which is -27 plus 12 is going to be negative. So we answered all the questions there. But I put in a little, sometimes we call that, it's not really a free body diagram. It's a directional diagram that when we start here at t is equal to 0, we're at -9. So moving to the right on a number line, we would be at x is equal to 7 at t is equal to 2. And then when you turn around at x is equal to 7, and then we go in the other direction. And there's not much more that we are going to talk about with that problem. And there's nothing else that we can talk about. We can talk a little bit about acceleration at those times, but those are the only questions we are asked. Okay, so number 8, use the graph of the function to estimate the intervals on which f is increasing or decreasing. Also estimate the x-coordinates of all local extrema. Assume that the function is continuous. Oh, I thought that was a highlighter. So here, this is really important because we have a derivative, f prime, that is discontinuous. Sometimes students will think, oh, f doesn't exist at x is equal to 8. Oh, but it doesn't say that. It says that, assume the function is continuous, even at the points where f prime is undefined. The domain of f prime is from 0 to 8, you can see which, including 0, and then from 8 to 10, including 10. Okay, so with that. So what I did next to the graph is I highlighted the graph where above the x-axis, you have f prime is greater than 0, f is increasing. And then below the x-axis, I colored it red, and it's f prime is less than 0 below the x-axis, and f is then decreasing, okay? So here's what I did. And I took those numbers where I found, let me use blue here. I found where f prime is equal to 0 at these 3 locations. And you can kind of see f prime is equal to 0, right? At 2, at 6. Something happens at 8. F prime is not equal to 0 there. But something happens here, it becomes a critical number, okay? And then at 9.3. So I have those marked. And actually, I really, like I said before, I really like to put in some kind of demarcation that's a critical number, that's a critical number, critical number, critical number. And sometimes we forget about critical numbers where the derivative is undefined at that point. So it's important in this one. So where's f increasing? You can see I put the intervals that are in orange on the graph? And the answer is H. Where is the function decreasing? Where I have the shading on the lower part of the graph, that's from 2 to 6 and 8 to 9.3. The answer is C. Okay, and then I have what are the appropriate x-coordinates for all local extrema of the function. So the graph has local maxima, so you can see where I'm pointing to, and I do the little whoop whoop thing there. At 2, we have a max, and at 8, we have a max, where the function is, and I didn't mark it with increasing or decreasing, I could put this here, where the function is increasing, then it goes to decreasing, then the function goes to increasing, decreasing, and then increasing again. So you can see we have a max at 2 and 8, okay? And then we have local minimum at 6 and 9.3, okay? And here we're saying, what are the approximate x-coordinates of all local extrema? So I think we have everything, right? Now, I did highlight the fact that at 8, it probably looks something like a cusp, okay, where the function is continuous, f prime is undefined, and so forth. I think I have an f. It looks like I have a little f prime there, but that would be what the graph of f may look like, okay? And let me see. Go to the next problem. So we have a question number 9. Use analytic methods to find the local extrema here. So we're just going to, and then it says, use analytic methods to find the local extrema, the intervals on which the function is increasing, and the intervals on which the function is decreasing. So in this case, take the derivative, set it equal to 0, find the critical numbers. Notice I factored out a 2. It's not necessary that you do that. But then my input is going to be 2 times a negative and then 2 times a positive. So you can see that I have my derivative f prime goes from negative to positive. So my function f is increasing on the left interval and then, decreasing on the left interval and increasing on the right. So we know that a local minima occurs at 2, -4. Notice I put the function value in. That's a good practice to get into for your AP exam, showing your justification for how you got your point. And then for the second question, it says, I want to say the intervals on which the function is increasing or decreasing. So the function is decreasing from negative infinity to 2, including that endpoint, and then from 2 to infinity, it's increasing. You know this is not, but make sure this is not anything that you're going to really struggle with this problem, but make sure you show the evidence for how you're getting your answers on your test. Okay, number 10, use the derivative of the function y is equal to f of x to find the points at which f has a local maximum, local minimum, or a point of inflection. So now this is one where I saw some of your work and I made a couple comments on it, that if I have the derivative, I don't multiply it out in order to take the second derivative. In fact, I don't multiply it out right now to deal with the first derivative to set it equal to 0. And some of you had been doing it for both cases, for the first and second derivative, multiplying this out. So it actually turns out that the factored form is helpful because you can perform then the principle of zero products, where you just say AB is equal to 0, either A is equal to 0 or B is equal to 0. Okay, so when I look at this, I can instantly say, the critical numbers are 1 and 3. So the work that I'm going to do with this is I'm going to use the number line. I'm going to use the first derivative test to find the local, and that's what it's for, to find the local minimums or maximums. So now with that, I put y prime above the number line. And then notice with the first factor, I have it shaded yellow, or not really shaded, but highlighted yellow. So I take that first factor, I leave the negative sign in the derivative out front, and then I put a plus for all the first factors, and then I test the second factors. So I put 0 minus 3 is negative, and then go to 2 minus 3 in the middle, and it's negative still. And then if I plug in the 4, I have 4 minus 3, which is positive for the last interval. So you see I get those signs for y prime is plus, plus, and minus. Therefore, the function y is increasing, and there's a stationary point, but not extrema at 1, and then it's increasing on the interval from 1 to 3, and then after 3, from 3 to infinity, the function y is decreasing. Okay, so the answer we have for the first one, there's local maxima at x is equal to 3. Okay. And there are no local minima. And that's it there for the first question. The second question, it says at what values of x, if any, do the inflection points occur? Select the correct choice below. Now, so what I did is I did a little side work for this. And notice that when I took the second derivative, I didn't multiply things out. All I did is I said, oh, let's use the product rule with this. Let me bring it down here. So with the product rule, let me bring it down a little lower so you can see the function there. So in the upper left-hand corner, you have the function. And so all I did is I took the first factor. Let me say the first factor was here. I took that whole thing. And then the second factor, then I'm going to take it and color that in blue. So I have my first and my second factor. And you can kind of see, here's my first or second plus second. Here's my second. And then here is my first. So again, it's in red. So and my first is here. So first or second plus second or first, I can just leave it in that form. Now, the nice thing about this is that when you get really comfortable with factoring out binomials, and that's really going to help you if you can do that, because you don't have to multiply things out and then refactor them in the end. What you can do is factor out a -1 sign, because I have a negative and I have them highlighted there. I have a negative, the quantity x minus 1, that I can factor out, put that out front, and you can see that the remaining factors turn out to be x minus 1 from the first grouping, and then 2x, I'm going to factor a positive 2 now, 2x minus 6 would be left, which simplifies to give the second derivative here at negative the quantity x minus 1 times 3x minus 7, the quantity. So that's what I'm going to test, and you can see that I put that up here. Testing the second derivative, I get a negative, positive, and a negative for the signs of the second derivative, about 1 7/3. And then if you look in the bottom of that, then I've got separating the number line here, then the graph at y double prime is less than 0, so the graph is concave down. Then on the next interval from 1 to 7/3, y double prime is greater than 0, so the graph is concave up. And then y double prime is less than 0 on the interval from 7/3 to infinity, so the graph is concave down. So we're now ready to answer the last question there. So we have, at what x values, if anything, do the inflection points occur? When you have to note, whenever there's an inflection point, you must note that there's a change in the concavity. So you can talk about y double prime going from positive to negative about a particular point. That's very important for the AP exam, that when you say that it is an inflection point, you have to support it, not with that whole number line, but you're actually going to have to say x is equal to 1 7/3 because y, oops, wrong pen, y double prime changes sign. And you can say how it changes, but at x is equal to 1 7/3. Okay? All right, and for question number 11, I know the video is getting a little bit long, we have find the extreme values and where they occur for this graph. There is an absolute max, and it's also considered a local max because it's higher than any other point in this little neighborhood. If I would highlight this, in this neighborhood, that's the highest point, 0, 6. But if you notice at the bottom where there's a hole, there's no minimum value. So we have the absolute max here at 0, 6, and then there is no absolute minimum. And you can kind of do this, you can picture zooming in at this point, at that end point. There's not going to be a min, because as you continue to zoom in, there's not going to be a lowest y value. You're going to be able to see it gets lower, lower, and lower, and lower. So no minimum there at negative 2, 0. Now then identify the local maxima for part C. Local maxima that are not absolute maximas. There aren't any, okay? There are no local that isn't an absolute max. Okay. And then the last one, identify all local minima that are not, again, there's no local minima and there's no absolute minima at that lowest point on the graph, okay? There just isn't, all right? So there's that one, and then you have your answers that you can go over. Okay, then I'm going to let this be the end of Chapter 4, Part 1, Practice Exam Solutions. And if you have any questions, please send me an email quick, okay? Have a great night. See ya, kids.